a 15-minute video from a conference, I think from 2019, that was called All the Problems of Flat Earth, which essentially is focusing on the sun and the sun angles and using Eratosthenes as like the heralding example. So we're going to go through it in detail. And first, we'll just define our terms, right? So again, it seems basic, but we're going to be using these terms quite a lot. So we want to make sure that we define them. So we got circumference, the distance around the outside edge of a circle. All right, notice the definition says circle, right? Not sphere, just says circle. And then we look to the diameter, which is the distance across a circle that goes through the center of the circle. It's this right here. And then we have the radius, the distance halfway across the circle, right? Which is equal to half of the diameter's length. So radius, diameter, circumference. This is all parts of a circle. We're going to be using that exclusively, right? At the end, we're going to use, mostly all the way through, we're going to be using these formulas as well, so we can transfer between them, right? If we have an area or if we have a radius, then we can get an area. If we have circumference, we can get a radius, etc. because of these formulas, right? For area, it's pi r squared. Circumference, just 2 pi r. Diameter, of course, 2r, right? So using these relationships, we'll be able to multiply back and forth to get solving missing components of our circle, right? So when we're talking about Eratosthenes, the story goes, and we're gonna go over it a couple times, so I'm just gonna briefly touch on it here. We're gonna be measuring the supposed circumference of a circle, and he's gonna say that circles the Earth with almost zero evidence. And he's going to be using basic math and the units of a component of a circle, saying that a circle, of course, has 360 degrees. Therefore, he's going to use the measurements he took of the sun and the difference between the angles at 7.2. He's going to do 360 divided by 7.2. And all of this is arbitrary, right? This doesn't equate to anything on the Earth. 360 degrees of a circle and 7.2 doesn't tell you anything. The only thing that links it to Earth is this measurement right here, which is supposedly a geodesic arc length, right? This is 800 kilometers, the distance between these two on a sphere. That's what this is supposed to be. And that is the only thing relating this whole experiment or measurement or whole experience to the Earth in any way whatsoever. So we're going to be focusing on where they got this number and how that was confirmed much later on. But the basic premise is that 360 degrees.
Hey, before you continue, do you want to hit a glass of water? You got super.
No, I think
you got super raspy. Oh, okay, all right. If you're good, I'm good.
I can try. Hold on. Yeah, all right. So let's see if that goes better. So
much better.
Here we got 360 degrees over 7.2 degrees times 800 kilometers, which is the distance between these two cities. So the only thing that has any merit and metric that is tied to the world is this figure. And he, of course, in the story, this is just a known, right? Everyone just knew this distance. There's no method of calculation. You have to look into it a little bit further to see exactly the method that was used to determine it, but we'll go into that later. In the story, this was known. He did the brilliant math of just taking this 360 degrees divided by the difference times the difference in distance, and he got 40,000 kilometers. But in reality, it was like it was in stadia, so that was their metric of component, but we'll also get into that conversion later and how that can be skewed. But the basic premise right here, sun angles, difference in the sun angles between two locations, 360 divided by the difference times the distance between the 2 points gives us the circumference of a circle. And from that point, he just proclaimed this circle was the circumference of the spherical Earth. So we can look over here as another depiction of it, really, right? So if he's on this curved surface, these are the known positions. Here's the well that he was at, looking at on the solstice, which of course was on the tropic, which is how he could do that. And then he was comparing it with the difference over here. And the main point of this main component of this slide is assuming parallel sun rays, right? That's a big part. Or assuming near parallel sun rays, because they say that they're almost parallel enough where it makes our non-points meet in the distance, but not actually parallel because they do converge at a point way back here somewhere, right? So this is a little video that actually I stole from Karen B. Total honesty. She played this on her stream, and I was watching it. It's from 2019. It's from a Flat Earth conference. It's from a dude named Zach. I don't know if his channel was Dr. Zach. I've never heard of him. But I watched this presentation on what he called the biggest problems for Flat Earth, and I was enthralled by what he was talking about as a Flat Earther to present the problems, and I thought he had a solution for some of the problems, and then I thought that we had a solution for the other problem. So what he presented was a half solution, and I think that we have the other half to solve the entire problem. So we're going to watch most of this video, and feel free to comment. Do you guys have sound for this?
Yeah, real quick before you continue, question about Eratosthenes and the assumptions. Now, they tell us that it's about the assumptions made in regards to the distance of the sun with the parallel light rays, but really, it's about assuming the distance to Cyan and Alexandria, right? Like having those down before they could have even had them down in any reasonable way without some sort of geodetic surveying, you were saying?
Yeah, that is my ultimate conclusion, knowing with the detail that we do in this server about geodetic surveying, their adherence to predetermined spherical models based on the stars, adherence to spherical coordinates like long lat. So we're very skeptical of any distance so-called confirmed by geodetic surveying. And yeah, when you come down to it, the only part of the math that had any relation to reality that would tie it to any sort of grounding of measuring the Earth is the known distance measurement between Alexandria and Cyan.
Yeah, the only way they could have done that then, because like you know how the stadia is just a unit of measurement, but nobody really knows. But scholars agree that it's a ratio of the terrestrial meridian up to like 99.99% or something, so that it almost gives the agreement that like he was really close to measuring the exact dimensions or whatever kind of thing. But he couldn't have done that unless they already had it, because that's how it works. So it's not even, the story is backwards. It's not even about what the assumptions made of the sun. How did they have a coordinate system that used ratios of latitudes and longitudes where they could derive distances from that to have a distance from Cyan to that to do this, to make it relatable? The only way that would work is if they already did this. So we only have one piece of a story that doesn't make sense when you apply it to how you would have to actually derive this and what the assumptions are.
Yeah, talk about circular reasoning, right? This is the de facto measurement where we know independently the size of the Earth. And how did they determine it? Well, they used the known size of the Earth.
But dude, that's that is
What? You use geodetic surveying to measure the Earth? No. That's what you do when you know that it's requirement that the dimensions are known previously, right? It's part of the definition of geodetic surveying. But yeah, interesting loophole or logic loop, I think, as we should call it.
Yeah, critical point in the argumentation that it's not just about what they assumed the sun and the parallel rays. They would have already had to have this assumed and measured out, but there's no documentation of geodetic surveying done or how they did any of this. Like the cliff notes they give for Eratosthenes and how they got the distances, they were like, oh yeah, we had these dudes with cartwheels and they just rolled them back and forth and counted. Okay, dude.
Right. Well, they had, we'll go into it later. They had specialists, which were essentially like markers. They were like, well, I guess you could call them Eratosthenes grad students, people that would just lay meter and do stadia based on pacing, right? Paces was the unit of measurement. They just pace around, count up to the ratio until they get the amount, and that's supposed to be tested. But these people just followed them around for this one measurement or whatever.
They just paced around and measured the Earth almost proportional to what it is. Nice.
Right, you guys are joking, right? We confirmed that Eratosthenes was a real person, right? We have primary,
zero primary sources, which we'll also get into near the end. The only way we know he exists is that other fake Greeks cite him. You got Herodotus. You got the guy who Ptolemy stole Geographia from. He claimed Eratosthenes. All you have is vague references to this wonderful measurement of how everyone knows the Earth is a sphere and how we know the dimensions of it, right? But we're going to be arguing that we can confirm the circumference measurement indeed, but if you're at a dude standing in the middle of a plane, seeing in the dimensions of a circle or a sphere of 3959, then the measurements you take of the sun would be identical, and that what you would come out with is a circle of the sun, which we can denote as the exact same measurements, right? 24,901 mile circumference can be easily denoted and related to the sun's light on the Earth from this sort of position. But let's watch the contextual video from our dude Zach here as he outlays why this is a huge problem for flat Earth and why most of mainstream media says it is, right?
You know, the reason why I want to do this is because not too many people know about these problems, and I know that if you want to solve a problem, you have to face it, because if you run away from it, you will never be able to solve it, and the problem will remain in the same place. So whenever you take a step forward, it will pull you back to your place. The problem itself is talking to you. It's telling you you cannot go any further without solving me. So what is the biggest problem with the flat Earth? If you want me to put it into one word, I will say angles. Anybody who really investigated the flat Earth has come to this, and they all found it as a big wall. None of them could go through it.
I would say the sun.
But if you are a fighter, like me, you will keep digging and digging until you make a little hole in that wall, and then you will finally be able to go through it. What I'm going to show you right now is how to draw this globe Earth model from scratch. Because if you know how to draw this from scratch, you will know how to draw this from scratch. You will face the same problems as they faced before. So you have to know how they made this globe Earth model from scratch so you can understand how to do this flat Earth model from scratch. You would start with is the sun, because it's the most powerful light you know, the most powerful light you see, so why not? So what are you going to do with the lights of the sun? You're going to place a stick perpendicular to the ground, all right? And then you measure the shadows, and then you will realize that the shadows draw half circles, different half circles throughout the year, all right? The sun goes farther away and it comes back later, all right? Well, anyway, so as you got smarter now, you would want to do something. You would want to know the shape of the place you live on, right? So here is the problem. You only have a tape measure, a shadow, and probably your brain. What you going to do with these things? Can anybody tell me? This is all you have. What you going to do with them? How are you going to know the shape of the Earth and you only have 3 things? All right. At that time, you only you probably believe that the Earth is flat because that's what you see. All right. So the first thing you might want to do to understand the universe is to measure the distances between us and those lights in the sky. And how are you going to do that? You're going to need at least 2 sticks. All right. So you're going to put them far away from each other. All right. As far as possible, because the sun is obviously big. All right. So imagine the distance between these two sticks is 2,074 miles, and the angles of elevation is 75 degrees in both sides. Then the distance to the sun has to be 3,870 miles, and that's the math behind it. All right, that's the math behind it. It's so simple. So if you do this, you would want to tell everybody about it, right? Well, you're going to have a lot of trolls around you, and they will ask you. They will want to do the same thing. And here comes the next problem. Everybody is going to do the same thing. They will find different distances to the sun. Somebody's going to find the distance to the sun is 3,000 miles. And somebody else will find it 2,000 miles. So you will want to do the experiments again, but in a different way. So check out this diagram. So what you see here is land. This is actually land, all right? And this is the sun. We don't know where it is. So it can be anywhere. And these are the angles of the lights during the daylight. 12 hours of the day, or in this case, 10 hours. So anyway, if you are right here and your friend is right here, both angles are 75 degrees, then the distance to the sun has to be, like I said before, 3,870 miles. So now, if you want to do the same thing, if you want to do the same thing with many people from different places on Earth at the same time, and imagine you have this guy right here is going to triangulate the sun with this guy right here. So they will have the sun at an altitude that is, I cannot even see it from here, but anyway, it's going to be lower than the first one. And the guy right here is...
Whoa.
Oh, the guy right over here is going to be like, no, man, you must have...
Oh, I nailed it.
Somebody else. The sun is way above my head. So you as a geometry guy, and I say geometry guy because all they know is what they have on the paper. They don't know what's going on in the universe. So as a geometry guy, how is this possible on a flat Earth? If you believe on a flat Earth, this is not possible. You cannot have too many suns. You only have one sun. So how are you going to solve this? Can anybody tell me how you are going to solve this problem? Because this is a really big problem for flat Earthers. Tell me.
It's an apparent position, the sun.
The sun is in what?
It's an apparent position, like a personal frame of reference.
All right. So how are you going to solve these angles?
This is 2019.
All these angles have to go to one point. Because if you are in a hallway, and you put a bulb, for example, right here in the middle, all right, and you go somewhere and you measure the angle of elevation of that bulb, you will get a distance to that lamp, all right? So if you go farther away and you do the same thing, you will get the same exact distance to that bulb. This is how it works. But in this case, it doesn't work like that. Something is wrong with this. These are real angles taken from real life. I didn't make them up. You know, if you measure yourself, you're going to find the same exact angle. So you're going to have three options. There is no four options. You're going to have three options as a geometry guy. The first option is keep it flat and do something in the sky, which is not the case, because if you look up in real life, you're not going to see anything, just clouds. So you're going to dismiss this. And then you will go to the second option, which is curve down the Earth. So these are, let's say these are the real elevation angles, all right? When you curve down the Earth, you can see that the elevation angles, they diverge from the top. And eventually they will become parallel to each other. And in this case, we will have one sun, because all these lines will never intersect anywhere because they are parallel to each other. But if we claim that the sun is too big, then maybe, you know? So in this case, you can say that we are solving the problem. But if you rely on these two pictures, then you have too many suns. You cannot solve it that way. And the third option is concave. So if you curve the Earth up like this, you will have a bigger problem than the flat Earth. And this is a message for concave earthers. If you think that the Earth is concave, then you have to solve this problem. And I know that you don't know what I mean by this, but if you continue watching, then you will know. So you go back to your globe, and you look at it. And you look at it again, because you don't understand. I mean, you're not solving anything here. So what do you want to do now to solve this problem? The first thing you will think about is measure the distance between these lines and make it match with reality. You have to make it match reality. So how are you going to do this?
Right, which you already know the distance between those two.
Smart. We all know him, called Eratosthenes, a guy with a cell phone. Here he is, so smart. This guy measured the circumference of the Earth. So when you measure the circumference of the Earth, of course you will know the distance between these two lines. So how did he do that? You all know the story of Eratosthenes, or should I repeat it? You all know it, right? Okay, good. So, anyway, before being as smart as Eratosthenes, you have to go through some geometry lessons. I don't know if everybody here knows geometry, but if you don't, I'm just gonna show you something really small here. I mean, it's not a big problem. So before being as smart as Eratosthenes, you're gonna take a globe like this, or a circle, or you're gonna divide it into 24 parts. Some of you will ask me why 24 and not 27 or 200 pieces. 24 hours. It's just, let's say, it's like when you say the circle is 360 degrees, okay? It can be anything. For example, this protractor right here is 400 degrees. So it's just a unit. Even if when you change the number, the circle is still the same. It didn't get bigger or smaller. You don't change anything when you change the number. So it's just the unit. Just like when you say 1 mile equal 1.6 kilometers. The distance is still the same. The number has changed. We're just playing a game here. So they chose 24 hours for some reason. I don't know it. So when you divide the circle into 24 hours, you get 15 degrees in each angle, all right? So 15 degrees is a good number. So when you know this, you have to do something else. You're going to draw a line from the center to the sun, all right? So that line is going to take you directly to the sun, right? So if you want to measure the angle of the sun, it's going to be 90 degrees. It doesn't matter the shape. I mean, it doesn't matter the size of the ball. It doesn't matter how big it is. So if you go to the next angle right there and you draw a parallel line to the first one, you're going to get 75 degrees in all scales. And I don't know why, because this is how the ball works. So in fact, these are 4 balls, all right? All these angles measure the same, as long as you are drawing parallel lines, okay? They measure the same. The first one is 75 degrees, the second ball is 75 degrees too. So they all work the same way. It doesn't matter the size of the ball. This is really important. So here is so Eratosthenes wants to know the real distance from for example, let's say I am here and the distance is, the angle of elevation is 90 degrees, okay? And somebody is somewhere, his angle is 75 degrees. If we measure the distance between us, it has to match our model. So our model has to match the reality. I mean, if it doesn't match, then our ball is not reality. So we have to create another model. So Eratosthenes was here, all right, in Alexandria, and he sent his friend to Syene. His friend is named Mycenes. Well, I just made it up. Because, all those names, you just have to add Aenes at the end, and that's it. Mycenes, Carones, something like that. Anyway.
This guy gets it.
Yeah, that's all. Anyway, so that guy had the sun as 90 degrees over the wall, all right? So they measured the distance between them. It was 500 miles. And the angle of Eratosthenes was 7.2 degrees, and I call it the angle
500 stadia.
Because it's not the angle of elevation, but it's almost the same thing. So what he did was divide 360 degrees by 7.2, and he multiplied it by the distance, and he got 25,000 miles in circumference. Very nice. Very close to our circumference, 24,901 miles. So,
like that.
If you look at this information, what do you understand? Nothing, right? Does anybody understand anything? I mean, if you tell me.
Well, they basically presuppose the Earth was a globe based on how
Great. So what are you going to do with this information? Imagine you are a friend of Eratosthenes and he gave you this. You're going to look at it and you'll be like, what the hell is that? And all I see is a bunch of lines in a circle. I mean, it doesn't make any... Tell me. I didn't hear you, swear to God.
Very big sun.
A big sun.
A big sun. Yeah, well, the size of the sun doesn't... but the size of the sun doesn't matter. I will explain it later. All right, so I'll explain it later. All right, so if you give this to anybody on Earth, they will look at it and they will be like, okay, only astronomers will use these angles. I mean, nobody uses angles. Who uses angles? Astronomers and a bunch of other crazy people. That's it. I mean, that's it. What are you going to do with this? Nothing. I'm just kidding. Anyway, so you will look at it and you will be like, this is nothing. But I see everything here. This is reality. This is the world we are living in. I see the future. I see everything here. So the first thing I will want to do with these numbers is draw the map. Everybody's going to use the map. The map is the future. If you don't have a map, you have nothing. So at that time, you don't have a map, so you're going to need a map, right? I can draw the map using these numbers. Can anybody tell me how? All right, so anyway, imagine this. Imagine I am this guy, okay? I'm standing right here, and this is a big paper, and the sun is right above me, all right? And we're going to stop the time. The sun is not going to move. It's going to stay there all the time. So I'm going to be here, and I got a friend beside me. I'm going to tell him to blindfold me. His name is Mike Kavanaugh. I'm going to tell him to blindfold me, all right? And just keep walking in any direction because I don't want to see him, all right? He's going to keep walking and walking and walking, and then he's going to stop somewhere far away from me, very far away from me. And then he will call me on Eratosthenes' cell phone. We have to use Eratosthenes' cell phone, by the way, because if we don't do that, we have to wait for next year, and next year is going to take us a lifetime.
And nobody knows how they communicated this.
Eratosthenes' cell phone, and it's okay. So Mike is going to go to that direction. He walks kind of like this, and then he's going to stop somewhere. He's going to stop somewhere, and he's going to pick up his phone. He's going to call me, hey, dog, I'm here. And I will ask him, what is your angle of elevation? Mike is going to measure his angle of elevation. He's going to be like, I think my angle of elevation is 75 degrees. I'll go back to my position. All right, so 75 degrees. I'm going to come to my drawing. You can use this one or this one. It doesn't matter. It's the same. So 75 degrees, Mike is right here. All right, so I'm going to know that the distance between us is 1,037 miles. That's the distance between me and Mike. I just knew it by using the angles. So I know the distance to Mike, and I'm going to confirm it because Mike already measured the distance while he was going there. So Mike will be like, what is the distance to me? And I'm going to be like, 1,037. He's going to be, oh, man, I just measured 1,036. How did you know that? Man, I got it right. I'm just kidding. Anyway, so...
Asshole.
Hey, you wanted to make fun of me? There you go.
Thank you very much.
Yeah. So the distance between us is 1,037 miles. Do I know where? I'm going to ask him about the place, of course. Where are you, Mike? Mike is going to be like, I'm in Egypt. Okay. So I know the distance to Egypt. Do I know what Egypt is? No. That's correct. I don't know what Egypt is. I just know the distance to Egypt. So if I want to know what Egypt is, I'm going to need another angle. What is it? The angle of azimuth, the horizontal angle. I didn't use it yet. So we only used the elevation angles, and the elevation angles can only tell me the distance to that guy. That's it. And I want to know I want to triangulate that guy. So I'm going to need another angle, which is horizontal. So how the hell am I supposed to do that? I'm going to call Mike again. Hey, Mike, do you have a compass?
Oh, there is a compass.
Do you have a protractor?
Of course I have a protractor.
All right. Is it a big protractor or what?
Yeah, it's a big ass protractor.
Okay, Mike, you have to stand on it. So Mike is going to stand on that protractor. It's a big protractor. I'm going to tell him, Mike, you have to point 0 degrees to Polaris. Do you know where Polaris is? Do you know what it is?
Of course I know, man. I'm going to show him. You forgot it?
All right, so you're going to point 0 degrees to Polaris. So I'm going to do the same thing for my position. I'm going to point Polaris. I'm going to point 0 degrees to Polaris. All right, just like in this drawing. Look at number 1, for example. I have Polaris right here, but it should be somewhere else. It should be the line that goes to Polaris should be parallel to the other one. I just did it like this so you guys can see it. But anyway, he's going to point his protractor to Polaris, and I'm going to point my protractor to Polaris. And I'm going to draw a circle with a radius of 1,037 miles, which is the distance between us. Now Mike can be anywhere on that circle. He can be anywhere. He can be right there, right behind me. He can be anywhere. So if I want to know where Mike is, I'm going to try to move that protractor around that circle. I'm just going to move it like this, pointing 0 degrees to Polaris all the time, all right? And I'm going to draw a line from his feet to... No, first I'm going to ask Mike. Yeah, I forgot this. First I'm going to ask Mike to tell me where the sun is, because the sun is right above my head, okay? So Mike is going to be like, I don't know how to measure that. I'm going to show him how to measure the distance, the azimuth of the sun. So Mike is going to be like 1, 2, 3, 4, 90 degrees, 3, blah, 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 180 degrees, blah, 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 270 degrees. So the angle of azimuth of the sun for Mike is 270 degrees, all right? So I'm going to draw a line from his feet to 270 degrees. I'm going to keep doing this, just like in the picture. That line is not going to go through me, and I want it to go through me because there is only one point on that circle where that line is going to go through me. So I'm going to keep moving that protractor around that circle, and eventually that line is going to go through me. That's where Mike is. There is no other point. Mike is going to be there for sure. So I'm going to know that Mike is right there. If I walk that way, I will find Mike. Maybe I will be a few miles off, I don't know, but Mike has to be right there. Now I know where Egypt is, and I know where Mike is. All right? So the way I found Egypt, I can find Morocco. I can find any other place that is close to me. So this is how I can map the world. If this line right here is parallel to this line, then I'm going to draw the UTM grid system. That's what I'm going to draw. Then I'm going to wrap it around a globe. All right? But do you mind
that's universal transverse Mercator.
Especially the part about Mike. He must be a really cool guy.
Yeah, I know. All right, so now you know where Egypt is, and you can draw the entire map, especially the countries that are around you. All right? So is this all? You will find another problem. The problem is, if you want to draw other countries like, let's say UK, all right, let me say I want to triangulate London, all right? So I'm going to send somebody. London in my, if my calculations is right in front of me. So I'm going to send somebody there. It's not going to find London there. I'm going to be asking myself, how can I find Egypt and Morocco and all countries are close, and I cannot find London in the right position? That guy is going to go left, he's going to find London, but the distance between us is still the same. What's going on? I mean, if London is right there, and I'm telling you this because I did it before. London is right there, and we have, let's say, a distance like 5,000 miles. I'm not even sure. So if that guy goes left, the distance is still the same, but London is here, it's not here. So there is something wrong with the azimuth, because the angles of elevation are working, because the distance is working. But the direction to where London is not working. So what am I supposed to do? How the hell am I supposed to solve this? We have to find a solution. So as a globe earther, we have messed with when we did this, we messed with the angles of elevation. All right? We messed with the earth. We curved down the earth in order to fix these angles, to make them look parallel to each other. All right? And that's how we fix these distances. So if we want to make the azimuth work, we have to mess with something else. So what are you going to do in this case? And this is just my theory. I think they tilted the earth 23.4 degrees to get to north, and this is how you can make the azimuth work and finish the globe. Of course, the first map is going to look like a mess. You have to adjust it and adjust it until you finish it, right? So this is how they draw the entire map. And once you draw the map, what are you going to do next? You still have problems. And these are all problems of the flat earth, all right? If you are a flat earther, you have to focus on these angles. Because if you know how to deal with angles, the way they draw the ball earth map, you can draw the flat earth map, or it's not going to be easy. They tilted the earth, you have to do something to the earth, because I already solved the problem of these elevation angles, and I couldn't solve the problem of the azimuth. Not because it's impossible, it's because I couldn't do it yet. I'm still trying. So once you draw the ball earth map, you're going to have another problem. This is the next problem. This is what I was going to tell you. How many people think that this is correct? Nobody. And how many of you think that this is correct? Good, everybody. Because this is the truth. This is the truth. They know it. They know that the angles of elevation come from the center. They know it. Don't think that they don't know it. All right? And this is why they put the sun so far away. It doesn't matter the size. See the size right here? They deal with the sun as one point. They just care about the center of the sun. All right? They only need the size when it comes to the eclipse. But when it comes to angles, they only deal with the sun as one point. Because the size of the sun can be determined while you have the distance. If you have the distance, you have the size. If you have the size, you have the distance. That's it. If you modify the distance, you have to modify the size. This is how it works. So if you put the sun right here, look at these angles. They don't look parallel to each other. But when you put it far away, they start to become almost parallel. So they put the sun 93 million miles away. So of course, they will look parallel. If you draw lines from 93 million miles away from the center of the sun and make it so small, it doesn't matter the size. You're gonna bring those lines from the center, just like this, and you bring them to Earth. These lines will look parallel to each other. That's why I told you the size doesn't matter. You know? So this is how you fix the problem of the angles. You have them parallel to each other, and at the same time, they are intersecting somewhere, because they will just look parallel from Earth, but they are not. So this is how they solve this problem: one sun, one Earth, and the angles are working. Isn't this genius? It's a globe model, I know it, and I'm a flat earther, but this is genius. They fix everything. They fix the azimuth and the elevation angles and everything.
They basically trick
Yeah, of course. They are exactly. Well, they are. They don't say they are parallel 100%. If you look at it, look it up, they say they are close to parallel, not 100% parallel. They put it far away because from here, if you measure the angle, it will be like, let's say 75.00001.
Yeah, just like parallax angle. It's got to close that triangle.
They did this trick. Of course, it's just a trick. So now, from that time, the distance to the signs was like 3 million miles away or something like that. It wasn't that far. All right. So, of course, if you put the sun 3 million miles away, the math is going to work with everything. But when it comes to the eclipse, they find that, they have to play with the distances because something is going.
All right, so that's pretty much most of it. He goes on to go about the eclipse and how they changed the solar diameter, which changed the total duration, which changed the distance, which ultimately means that they had to resize the sun, right? And then they made that go away in the news. But yeah, he's right. The whole model is based on the optical diameter of the sun, and the whole Eratosthenes example of rebuilding the map based on sun angles is a really good way to think about it, right? Because we know that the Gleason's map is a sun calculator, right? We know that you can use the sun angles on it to deduce longitude, and you can take an actual angle measurement with the given articulator arms in there to get a real life measurement to compute distance, right? So we know the scale for 69 miles per degree works north-south only and not east-west. Now, when he was describing how to draw the map and how to get the angles, the azimuth, right? If you're trying to think about the world as a Gleason's map, an azimuth or a bearing, a direction, right, can't be a straight bearing. It would have to maintain a circle. And that's where it's going wrong with the mapping, and how he said that he couldn't find a city if you go based on the direction. Of course, the azimuth will be wrong. But I thought that was a really good sort of breakdown of all the problems for flat Earth and how he did Eratosthenes from the ground up, essentially drawing a circle, putting it in pieces, right? I mean, this is how they want us to interpret it, but obviously we have a different framework of interpretation. If we are on the flat Earth and we just observe a hemisphere around us in the same dimensions as the globe, right, then we would observe the same sun angles. We would have the same measurement of circumference of this sun of the circle over here. And he said the other important thing was that to fix it, they had to tilt the whole model, and that's absolutely true, right? So the other thing that people don't accredit our boy Eratosthenes over here with, he's making his globe model on the right here, but what they don't accredit him with is literally the axial tilt. You're right, he created it himself. Hold on one second.
Single-handedly came up with the wobulation axis?
Yeah, like, so when the fake Greeks invent stuff, they invent them like in a group. Hipparchus and Ptolemy, they all invented the tools for each other to create the backbone of the globe model that no one will use for 2,000 years. And that's a real life picture of Eratosthenes doing so with, this is actually the inspiration for spherical long lat. If you look up Hipparchus's account later, he was so enthralled with Eratosthenes' quote measurement of the circumference of spherical Earth that he then was induced to lay down the groundwork for spherical trig and all of that good stuff. But the way that they attribute him with the the quantification of axial tilt, right? Like, oh, he measured it so well. What we didn't concentrate on, but I think I tried to mention, is that Syene is actually at the Tropic of Cancer, right? The place with the well, which on the solstice would show the sun totally vertical at 90 degrees, was on the Tropic of Cancer. So that makes total sense, right? To map out anything, you'd have to know that. And that's why he said, to start, you start with the sun, right? And I think I would agree. It's the only way to, be able to center and measure things when you don't know 90% of the ground and it's mostly water. But he said, so because of this, right, he quantified it by knowing the sun's maximum altitude at Alexandria during the winter solstice, and by knowing the sun's equatorial position, which is zero declination during the equinox, and then also by knowing the difference between solstitial angles and the axial tilt. So he knew all these things, and then of course this is the math to get the variance of the axial tilt, and then you get the angular difference. And he was like, oh man, Eratosthenes derived the tilt with remarkable accuracy, all from assuming and needing parallel sun rays, and also knowing that Syene's on the Tropic of Cancer. Now, how lucky would you be to happen to have a location at the exact spot where you would need to rotate the whole Earth to get it to match the ecliptic rotation of the sky to then solidify a spherical coordinate system to base it? I mean, what luck, but they're all pretty lucky, I think. So if we go back to our position, that this is a valid position over here, this circle would be equal to this circle in every goddamn way. especially because you're taking measurements of the sun and you're looking at shadows and you're measuring the distance and the travel of the sun. You're using the sun actual the ground position speed. Was it the what do they call it? The actual speed of the sun over the ground, to measure distances. That's where that 1,000 miles every 15 degrees came from, right? Because the sun has an annual speed of around 900 miles per hour. But if you look at the same application of a circle here, we have the same diameter, right? The same radius and the same circumference, which are all equal, which is what we started with. So what we're going to do later is we're going to backwards derive our circumference the same way that they kind of derive their circumference from supposedly the sun, right? And of course, they got their important circumference from the sun, and only from the sun, and from sticks and shadows. Again, can't say it enough, the only thing that they measured in this experiment were these two angles, and everything else was assumed. Everything in gray is assumed, right? So to calculate a circumference of an unknown circle and then say it applies to the ground because of reasons is quite a leap. So here's the Wikipedia representation of it. Here's how we would know. Here's the math again, right? And again, this is calling attention to the only two things that we know is these two measurements, right? To get this value, which again, when we're dividing it by a known distance, is it. That's the only portion. That's the only time that matters. Now we got one more quick video. I think it's 2 minutes on I think a well-known mathematician who was interviewed for some dude's channel about how we know all the astronomical distances in the universe and how cool it is. And I think he did a really good job visually explaining it. But they also go into, hey, how do we know the distance between Syene and Alexandria in the first place? Oh, no. It's not loading. I can fix that.
I knew it. Shane doesn't want us to know.
No, it's a really good video. Hold on, let me see where I put it. Oh man, you know what? When I downloaded it, it gave me a really weird error. Oh, and I couldn't steal it for some reason. So then I had to like quote it. Crazy.
There was some theft protection on it or something. What happened?
Yep. So I couldn't steal it. Let me see if I can get it now. Yeah, there it is. I think it's right at 4 minutes. Perfect. All right. Let me share this then instead. Real quick. Switch it up. Change windows. Okay. Can you guys see this? Am I sharing the right thing?
Yes.
All right.
Terrence Tao on how we measure the cosmos.
Yes, perfect. All right, it's right at 4 minutes, so here we go.
And
can you hear it?
You need telescopes, sextants,
yeah, we have
spacecraft.
All right, cool.
You just need to look at the moon.
Something else very cool revealed by these kinds of compositions is how you can just see the relative size of the Earth and the moon. We'll get to that in a moment, but first things first, how do we figure out how big the Earth is?
The first person to do this that we know of is Eratosthenes. The way the story goes is that he had read somewhere of this well in this town called Syene, where on one day of the year, the summer solstice, you could look down in the well and you could see the sun reflected in the water underneath. And he said, oh, that's kind of cool. I don't live there, but I have a well in my own town, Alexandria. I'm going to go try the same thing. So he waited until the summer solstice. At noon, he went down and looked at the well, and there was no reflection of the sun. So I think, like, if you're a regular person at this point would say, oh, you know, that story is fake news or whatever the film was at the time. Sure. And he knew from Aristotle and the others that the Earth was round. The reason what was happening was that the sun was not actually vertical.
Let's think of the sun as far enough away from Earth that all of its rays of light are effectively parallel. At any given moment, if you draw a line...
Effectively, right? Never really parallel.
The sun, it passes through some point on the surface, which must be experiencing this phenomenon, where the sun is directly overhead. But if you were someone in Eratosthenes' time, it would be very difficult to know exactly where this was happening at a given moment. So what makes the summer solstice special is that on that day, the axis of Earth's rotation is tilted directly towards the sun. And as a result, on this day, as the Earth revolves around that axis over 24 hours, there's a consistent line of latitude where all of the locations on this line predictably experience this phenomenon, where at high noon, it's the highest of all high noons, where the sun is overhead. This line has a special name, it's called the Tropic of Cancer, and the town Syene that Eratosthenes had read about sits on this line. Now, Eratosthenes himself was a bit further north than that, in Alexandria. So on that day, at exactly noon, the direction he perceives as straight up, which I'll draw with a pink line here, is not pointed towards the sun. It sits at some angle with all of those rays.
He had what's called a gnomon, which is kind of like an ancient protractor or sundial, a portable sundial, basically. He measured that the sun was actually about 7 degrees off of the vertical.
Critically, because he could also know that at this exact moment, down in Syene, many, many, many miles away, the sun was directly overhead, he deduced that this means the arc length along Earth between Alexandria and Syene is about 7 degrees. This, in turn, means the ratio between 7 degrees and the full 360 degrees of a circle must be the same as the ratio of the distance between those two towns and the full circumference of the Earth.
All right, so the only way this has physical meaning is if this ratio is real. So the only way that it has meaning is if you know the distance, right? That's what he's saying. So thank God we knew the distance for reasons.
Now keep in mind, in the records that we have, it's not like he's reporting this distance in miles or kilometers. The units they were using back then were stadia, where a single unit is something like the length of a stadium.
So the distance was about 5,000 stadia, which is about 500 miles.
How accurate is our conversion between stadia and miles?
That's a good question. We are not completely certain. So with the conventionally accepted conversions, I think the accuracy of Eratosthenes' estimate is about 10%.
You can find sources online that claim his estimate was more accurate than this, but just keep in mind if you selectively choose which of the many possible conversions between stadia and miles to use, you can kind of p-hack your way into a better number here. Still, 10% is pretty good with no technology, but of course all of this hinges on actually knowing the distance between these two towns. So the natural question you might ask is, how would he know that?
This is not recorded. There are some theories. One is that there are merchants that go up and down the Nile. They
the
know
biggest hole in the story, huh? The most important piece of the story nobody knows.
And so from that, they have some estimate. The joke is that he basically hired what we would now call a graduate student to pace the distance from.
Dude, that's almost as bad as the super carrot theory, but we'll move on.
Rest in pieces, bro.
It's like a joke. They're like, well, good thing that he knew that, like, good thing we'd already established the geodetic distance between those 2 points on a sphere as an arc length, right? Good thing we already knew the unit of measurement tied to our graticule, so we knew that our actual measurement unit was a unit of 1/10 millionth of a terrestrial meridian of the same. So that, well, we had to know how long the distance was. Well, we'll just take a ratio of that terrestrial meridian. Duh. Like we already knew it, bro.
Dude, down to 10%. And he's like, and you could find even more accurate ones. It really doesn't matter, but like be reasonable with it and just go with the tenor.
Yeah.
Keep it low key, bro. I got you.
He's like, because you can be like aggressive in your stadia conversion to see which of the end of the scale that you want to loosely apply, and you can manipulate his ending circumference value to be more or less close to the actual value, right?
Yeah,
so
you can get right in there. Yep.
Yeah, or you can make it terrible, right?
Yeah, he hired grad students, bro, that just happened to use a coordinate system that confirmed the thing that they were trying to make.
Well, I mean, he says
Isn't
grad
that
students. Awesome? But like, I mean, I think he's just making that up. I think he said it's a well-known joke that nobody knows, and my theory is grad students or whatever. All right, then we can switch back to this. Everyone can see that, and we're good, right? Everyone sees the slides now again? Cool. So if you look it up, right, it says, this is the Wikipedia shorthand description of the story we've heard two to three times now. But he says, by knowing the distance between Alexandria and Syene, which was measured by professional surveyors called, what was it? Bematis. Called Bematis, right? Eratosthenes was able to calculate Earth's circumference. So thank God for Bematis. And so what are they? Well, if we look into it, right? And these are the dudes following Eratosthenes around with his sticks and shadows so they can make accurate measurements of paces. But if you look into it, It says no direct references. Actually, primary Greek and Latin texts from the era do not mention Bamatis measuring this distance. The earliest surviving description of this method comes from Cleomedes, that does not cite Bamatis. So we knew that they existed, so we just assumed that must have been what happened. They said they were often employed for military campaigns, but their direct role remains speculative. The round number and slight discrepancies suggest the figure was a simplified known approximation. Well, no way. So the actual conclusion is that, the Bamatis involvement is plausible. It's widely repeated. There's no actual evidence that this happened. So how do they confirm it? A rumor that some super specialized counters came along. The grad student lads? Nope, that didn't happen. It wasn't them.
Oh, the grad lads?
It wasn't them. It was a rumor. It was an unfounded rumor that some math Bamatis came along and really nailed down that measurement because they knew it for sure. And nope, that actually never happened. There's no evidence of that either. So onward to, do we have actual evidence that Eratosthenes, the story itself, is real? And the answer is a resounding and a hardcore no. Absolutely not. We have zero surviving evidence, right? Everyone knows that everyone knows. But it's like the whole evidence is, it is known. First-hand citations and ancient texts, meaning other people cited them. Cleomedes, Strabo.
First-hand citation, huh? That's fancy,
someone else,
bro.
That's like super hearsay, dude. Super hearsay, probably. Well, listen, we all believed it. Oh, okay, all right. So Strabo is actually the dude who Ptolemy stole his Geographia work from, which is the birth of cosmography, cartography, the birth of the two-sphere system, the relationship between the celestial and terrestrial spheres, all came from Ptolemy, who actually stole it from Strabo, who also referenced and therefore proves Eratosthenes. We have Pliny the Elder, who wrote a natural history. He praises his measurement, so that means that it was real, I guess. And then we have hold on. Theon of Smyrna, right, who had preserved fragments of Eratosthenes, analyzing Plato's mathematical philosophy. Wait, what? Fragments of a work by Eratosthenes, which was analyzing Plato. So he had a piece of a book that was definitely written by the guy who was proved to exist by this other guy who mentioned him, who also mentioned him in this book, who was known by this guy.
That's a first-hand citation to me, brother.
That is literally the accurate historicity of, did Eratosthenes really exist? Are these measurements valid? Anyway, just saying that's what we're dealing with. And for this whole presentation, we'll be dealing with them in the weeds.
Dude, real quick before we move on, can you go back a slide to my boy Strabo?
So
let me run down the chain of events for the graticule here. So Strabo came up with the lat long system, right? The merger of the celestial and the terrestrial spheres. And then Petals came along, swooped it from him, right? And then Walter Bislin came along and made the same thing. And then you came along and swooped Bislin's. So now there's just been a perpetual re-swooping of the same coordinate system for the past 400 years. Is that's been derived off of a mysterious assumption that requires you to actually know the dimensions of the place before you can even make the map? Like dude was saying, You basically have to trial and error it out and then present a narrative where you just one tap it on the assumptions of basic geometry. Is that kind of where we're at?
and at the end of it, you just look at it and you're just impressed and bemused, and you're like, look at the majesty of the globe model. Look, they solved every problem, guys. They in reality, but the guy in the audience was like, no, they tricked you. And it's like, yes, they solved every problem by cheating every single time. That's what
wicked smart.
We'll solve the angles by pushing it to near infinity, not real infinity, right? It's not too parallel. It's just how we need it to be parallel, right? And no one on Earth can verify the difference between 99.9% parallel and parallel. Right? Nobody can measure that parallax angle to the bottom of a right triangle, Alan, that isn't in the 10,000ths of a digit of accuracy, right? Nobody's gonna confirm that with human measurements. That's retarded. So they buried the details in that, and then they move forward. So again, this is how they want us to interpret it. But again, all this is giving us is a circumference, and the dispute then becomes how to apply that circumference value, right? And if we have a sphere of vision, then undoubtedly we have a circumference governing that limit. And if we live on a globe, then we have a circumference of the globe, right? And for a 6-foot observer on each of these circles, on a flat plane with a circle of vision or on a globe, you would get, for the distance to the horizon calculation, an identical metric, right? For a 6-foot observer on a flat plane, staring off based on the diffraction limit and Rayleigh's criterion, you'll have a visible horizon at 2.9 miles. For a observer on a globe of radius 3959, you'll use Pythagoras' theorem, the Pythagorean theorem, to calculate the distance to the horizon, which would end up being, for a 6-foot observer on the surface of that sphere, 2.9 miles, right? So you have the actual same distance to the horizon because we have the same circumference value, and they're almost, so the luck of the identical application is just astronomical, right? So let's go through first this physical breakdown. We'll go through this optical breakdown real quick, and we'll go over why they're equivalent and our whole position they're in, and how we can apply Eratosthenes to it. So we have our good old curvature formula, right? Our parabolic representation of what it would be to approximate the curvature of a sphere, right? This breaks down to, I think, d equal the square root of 2 times RH, but we'll really further break it down to 1.225 times the square root of the observer's height in feet when we incorporate feet to miles and break down all these units. But this is, the same drop rate, right? We're approximating 8 inches per mile squared. Here's what it is at specific miles via the integral. We have some really good, talented math lads in our crew who can figure this out on the spot. Like to trap globers with it all the time. What we should also add to our repertoire is this, right? This is the basic Google well-known formula for how you would get the distance to the horizon on the globe, and it's literally just Pythagoras' theorem, right? You're just solving for this length over here with this value over here, right? So you can solve it, figure it out, use some algebra, cancel it out. Once you over here, hold on. Dude, he barked from laying down. He didn't even get up. That's hilarious. I think he's cool. Oh. Oh, man. All right. So we should work this into our repertoire, right? It's the calculation for the geometric horizon on a globe. Sorry. It's the geometric horizon distance, right? Meaning that it's a physical place on a curve with a sphere. Oh, my God. All right. So we're equating it to a physical horizon distance, right, on a sphere, meaning that this is a actual place that is calculated based on the physical properties and dimensions of this sphere that you stand on. That is what we're calculating in this instance. If we go to our equivalent, it's optics based, right? So it's not curvature, it's not physical curvature. We're looking off into the horizon based on our diffraction limit of the human eye. You can only see a certain amount. When you're just at the surface, that's a very small distance. It's about 3 miles for your observer based on this basic formula for Rayleigh's criterion. If we use over here, we have it plugged in for the actual wavelength that we use to get 3959, but we'll go into that a little bit more over here. So the actual argument here is, here's how we would get the radius value, which would, of course, compute to our circumference value, is that we would plug in theta, which would be our angular resolution limit, right? It comes out to 0.2 degrees, which we can later use to replicate other optical instruments, which would be the same distance over here, right? So it would maintain proportionality all the way through. How we would apply this for looking at it here would be over here. We're standing on this sphere. We're looking out over here. We can compute based on the distance to the horizon over here. When this person would start losing visual information at the horizon, we can calculate going the other way. So we get our angular resolution limit plugged in here. We come back to 3959 approximately. What that looks like in practice over here, right? So we got our sphere, our observer in the middle, and we got our circle, our circumference that we're applying our known measurements from, right? So when we measure the sun, this is where we're going to apply it. So again, we have an equivalence between an optic derivation of a horizon, distance to the horizon, which would give us a radius for a circumference value, and we have a distance to the horizon using the supplied circumference value as well, using the same radius. So we have an optical equivalence, right? If you wanted to set up your spreadsheet to show that, here's the steps to show that. Here's what the formulas would be based on where everything is. Super easy. Again, if we wanted to physically depict what we were talking about before with the geometric distance to the horizon, here's how it would simplify. Here's another depiction of it. This is a really well-known thing. So when a Glober on TikTok challenged me on this, I was very confused that people don't know this. I think people in 24/7 Flat Earth Discord talk about it constantly. They repeat this value all the time, but they know all of this as well. So, I mean, it's really handy to pick up some of the basics. Again, here's a close-up shot of how we're deriving our circle value, right? And the equivalence when we're standing on top of it versus how we're using an optic equivalence over here. Something that we don't focus on enough that I think we should cover right here is the distance from an observer between spherical, parabolic, and linear information loss, right? If you notice, they deviate right over here quite a bit. But the thing is, this is really, really far away, and up to 100 miles, even linear, is indistinguishable from parabolic, which is indistinguishable from spherical. So all three of these things are hiding together up here, getting muddled, right? We have people using a spherical formula approximated with a parabolic loss, which is in fact a linear loss of information. Which we go over later when we're talking about this loss of information is linear, right? It's not parabolic. We approximate it linearly. There's some math we can go into, but that's not the focus of this presentation here. So when we finally usually lay out this position, which is foundational, we say, look, we have an equivalence between standing on a flat plane and a radius of 3959 and a spherical limit of vision versus a circumference of 3959. People, of course, next say, well, that's cherry picking, right? Obviously, that's the one circumstance that you happen to know, and you pick the math to work just right. There's no way that it has any meaning. It'll never work with other. Well, it's like, well, it works with a whole bunch of other values and circumstances and equipment. And really, all we're cheating with is saying that, hey, we need to use an actual angular resolution limit for an optical device of 0.2 degrees. And then you can fluctuate the wavelength and diameter to get different values that would satisfy that requirement. And if you do so within these ranges, you can get things that are for thermal imaging for astronomy, near infrared, large telescopes, high-res optics, extreme ultraviolet. All of that would apply. So again, we have an equivalence between the two models. Then we have living on a flat plane, looking out at our sun circling us in our visible radius of 3959, and we have living on a globe, observing the same thing, and then just assuming that this is the circumference of the circular thing you live on. Now, for us to have this equivalent understanding, what I'm saying is that the sun would trace out a circle on the map of equidistant, meaning that, if everyone sees half the sky, this circle would be half the area of flat Earth, celestially speaking, for everyone. Meaning everyone only sees half of the sky, so that this circumference you're measuring would be 24,000 around it. And wouldn't you know it, of course, that is the equatorial circumference, right? So that is the length of this circle on the Gleason's map. So when I say the circle of the sun, I'm talking about this specific instance. If you notice, this circle is about half the size of the map. And this specific observation is a 24-hour sun in Alaska, I think, right over here. And you can see it's paired up with where you would lose visibility of the sun, where it goes outside of your range to see it. It sets for just a moment, right? So that would give us this sort of visual scaling for how much of the sun you can see. So he's in Alaska. He barely sees it. It appears to set right when it's over here. So it would have to be only visible through here. And as it comes up through over here, you can see that he can maintain visibility through with it all the time. As it comes closer, it gets higher. So then that's how we know how close it is, right? We're judging the distance of the sun, and it's passing his circle over here. And just about here, it becomes invisible, and it sets right off the screen. right? So you can't see it anymore. That gives us a pretty good understanding of the size of this circle. And if you look at it, it's almost about half the map, which lines up with the globe model saying that you can see half the sky. So that's why the flat Earth model has to say you can see half of the sky. You can see, you know, the observed angles of the sun are observed in a hemispherical fashion over a flat Earth. That's what this is showing. So then, if we were to bring it back to Eratosthenes and what he measured, right? If we put a dot over Alexandria, and then we say a circumference circle of radius, you know, to a circumference 24,901 miles, should give us a radius of 3959, which would give us, you know, a diameter of about the same. So what we're saying is that this would be what he measured. So using the same measurements, not changing anything, not even arguing that it's valid for a flat Earth if you just use a local sun, because you get a covariant scaling method with the same size and optical diameter. You can get varying diameters and distances as long as you keep the same optical disc for the angular resolution. So what we're saying is that if you use all those observations as they are, as he took them, and you just apply it to a different circle, right? We started with the circle being arbitrary, then this circle would work with the exact same dimensions. Not to mention, if done at a certain, let's see, via the prime meridian here, would maintain the same distance relationship, because you could measure the distance between these two on this map using the same coordinate system. Of course, since it's just previously known distances anyway, you could compute it this way using the longitude scale of the Gleasons and get the same distance between Alexandria and Syene. So, I mean, what we're going to say then is that this is the circle of the sun, right? This is where the sun would appear. If we were to draw a circle of the sun's light on Earth, it would be half of the globe, or in this case, it would be almost an ellipse or a circle, because we can't just draw a circle like this on the Gleason's map. Don't forget, we have a scaling factor to deal with when we're projecting an azimuthal equidistant map like this. It gets worse the further south you go. So a circle that we're drawing would not be a circle like this. It would be further distorted. It would be distorted according to something called Tissot's indicatrix, which is this cool scaling model. And right, the way to understand this is all these circles are the same size. The further out you go, the more distorted it is, the more ellipse-like it becomes, right? So the only reason I'm bringing this up is, therefore, if you were to draw a circle on the Gleason's map of equidistant proportions properly distorted into ellipticity, as it should be, you would get something like the actual daylight map of where the sun would be based on Alexandria, right? So this is a properly scaled circle drawn on. If you were to translate this to the globe, it would be half and half. This is actually dusk, twilight, dawn, and a bunch of the other gradations that they say. But this is more or less a properly prescribed circle around where you would see Alexandria if you were to measure a circumference of 24,901 miles. And just again, to put it over here, this is the circle we originally draw. Here would be the properly scaled ellipticity distorted Gleason circle. So that's kind of my position on that, is that the measurements is just all they did was measure a circumference value, and then everyone just said, oh, look, it's the circumference of Earth, and we know this previously known geodesic distance that confirms it, and that's how we know that it's real. And we're just saying, oh, look, we know that it's a circle. We're applying that circle to the radius of the sun. Let's call it the size of the circle of the sun, which again would match exactly this, right? And if you're looking at it, is exactly this. This is the distance you would, be able to see on a flat Earth. And so that's what Eratosthenes, I would think, measured. That's how it keeps getting confirmed, because it's a valid measurement, right? People confirm it all the time. It's just the application of that measurement that people go awry with. So it's definitely repeatable. It's consistent. The only question is, what does it really mean? Right? Does it mean that that's the radius of Earth? Of course not. You keep looking at the sun, directly measuring the sun. How are you not extrapolating about the sun? How does your end extrapolation become directly about the Earth? It's distance of the sun traveled over the Earth is only way that they're doing it, right? So therefore, it's based on the sun. They say that they knew the distance between Syene and Alexandria, but all they knew was the speed of the sun, as we know, and they calculated it based on solar speed. That's what everyone does. That's what they did there. They tried to dress it up in history. So Moving along here, we have, of course, divergent rays being equal to the parallel globe rays. Everyone knows this position as well. If you move the sun closer, the angles become they match up with multiple observers. Now that's because angles to the sun and really any celestial angle comes down to this. You get, as our boy Viking put out, either you get globe space magic with parallel rays from effectively flat and distant surface casting shadows on a curved surface, or what it appears to be everywhere and what is measurable here in the lab frame, every empirical reality where every observer ever has recorded, diverging rays from an observer-dependent point source casting shadows on a flat surface. And again, these can be equivalent because they have varying frames of interpretation. So at the beginning, our boy Zach was talking about problems of flat Earth, and he said that we have no answer for the angles and that the angles are a problem. And my answer for that would be to put a sphere around an observer on a flat Earth, and then if you have a viewing radius of 3959, then that matches all known elevation angles. It gets known azimuths for the sun workout. Everything works. And they say that's derived from the globe, and we're like, no, it's just derived from the basic observation of the sun from which they built the globe model in the first place, right? So if we look at, again, the importance of the tilt, Eratosthenes happened to pick a town directly on the Tropic of Capricorn so that he could tilt the whole world to make the directions work, as Zach said, or tilt the whole world to know that the sun definitely has parallel sun rays. Then you know that this set the basis for, like, he solved the problem of seasonal cycles for spherical Earth. He solved the problem and laid the baseline for astronomical coordinate systems and spherical trigonometry, right? So by correlating Saiyin's zenithal sun with the Tropic of Cancer's latitude, deduced the tilt, a value enduringly validated by modern science. So, I mean, influences Hipparchus's work later on. I mean, they all just kind of represent each other. Everyone's discoveries help each other. All these guys together invented the globe in 220 BC, but nobody used it until 1700. Hipparchus laid the foundation for latitude and longitude. Ptolemy stole the model of the spherical Earth from longitude and latitude marked out in stadia from our boy Starka. I mean, it goes on and on. If we tie it back to our Globe Busters episode from, I think, last week, when we went over the constants and the big G, gravitational big G, wouldn't you know it that the only way they make sense of big G as a value, the only way it has any value, is to employ the known circumference value from Eratosthenes to get the so-called, density of Earth, size of Earth, weight of Earth. All that comes from those formulas we started with at the beginning, 2 pi r. So using big G, they can deduce, all because of Eratosthenes. Without Eratosthenes and a measurement of the size of the circle, then they have no correlation for a big G, which was, of course, derived off a torsion balance of two balls that were not properly tiered out, that actually had two variables that was measured in a resultant proportion that was mistakenly solved reciprocally for each other. It was the most ridiculous explanation for the big G that you can get. But what they use this for is they use Kepler's third law on mass dependence. We know this over here, using the orbital period, the semi-major axis, and the two masses. They use this actual Kepler's third law to determine masses of stellar objects. So all of this would be related to this wonderful measurement of Eratosthenes, which is definitely real. Again, if you were to do the math out, right, you would need Eratosthenes circumference, you would need the big G, you would need you would calculate the radius to get in the volume. You would need little g and big G and the radius to get the actual mass of the Earth, which is what they have over here. So we've deduced this last week, right, as a function of height and time. This, of course, they just made up based on the known parameters already, and of course Kepler's third law and a known periodicity and observation, which of course was based on Newton's dynamic cause when he stole Kepler's third law of the observed empirical motion of the planets and then algebraically inserted a dynamic cause from which to base the theory of gravity on, right? So that's where this comes from. And then this is deduced from Eratosthenes. So these are the three metrics of how they know everything about the Earth and how they get these values over here. And so that's the end of the Canva part. And then we're just going to go through some visuals real quick. on some other stuff to show the secondary part from our boy Zach. He said that he solved some of the angles, but not all of them. And I think that we can solve the azimuth issue and the direction. We'll just go over here.
And a friendly reminder to all our audience members to hydrate. It's good for your throat to hydrate.
Yep.
Well, I think you have to do this,
especially if you're doing a Prezi. It can be important to stay hydrated.
Do you hydrate with brush tail coffee?
Some people stay hydrated with brush tail coffee, and we're going to bring in the brush tail babe spokesperson, Liliana, to tell us about that later on.
All right. Yeah. So when we're talking about the sun and angles and azimuth, right? First of all, we have to maintain our circular nature of direction, right? Because an azimuth would have to be circular. Directions aren't perpendicular. You can't just draw a line in perpetuity. To actually maintain a proper east-west bearing on flat Earth, you have to maintain a circle. So if we were to use, let's take an observation of the sun from the south, Punta Arenas, right? Let's go to where they were. Way over here, I think. Southern tip. Right? No, other way. There you go. So when they say that, when you said the azimuth doesn't line up, that's because without this circular grid, this azimuthal grid over the observer, then the proper azimuth of the sun cannot be known unless you put a spherical limit of vision over you. And then that would follow the arcs of the sun. Then you're not going to be able to account for angles from the sun. Right? That's where they got the globe model from, is angles to the sun. And this is how it works, right? So from the observer's position, actually, let's see. Let's do it from here, setting and rising. So you'll notice that when they were, from the final experiment, when our crew was over here and the sun did this, all the globers were like, look, we got you, because over here it started to set. Not over here, where you would think it, but behind them over here, right? They start over here. We're probably going to look at it over here. Right. There you go. Set over here. Way behind them in the south. So from an observer's perspective, what that would look like is this, right? The arc of the sun that you have to maintain, that everybody sees in observable reality, is the semicircles that our boy started with, right? It does different semicircles. If you mark it with the shadows, you can see the same motion. If you look at it in the sky with time lapse, you'll see the same thing. This is the confounding problem of all flat Earth, is sun azimuth, which is why this model right here is so important for visualizing and understanding the spherical limit of vision, right? Without which I do not know of a way to make the sun work on flat Earth. Right? I don't know of any other way to do it. This is the only way it makes sense to me. So again, let's just draw it out here. Right. So again, way in the south, on Earth, the sun during this winter solstice over here rises south of east, right? Way out here. So almost behind them, if you're an observer over here, it rises south of east, does an arc in the sky, comes all the way back down. And again, this is this arc in this direction. Does an arc in the sky and then sets almost behind them, right over here. Sets way south of west. So if this is the bearing of the observer, which you can see, then you can tell that the sunset was way out there.
So as long as you incorporate your radius of vision, you can account for all sunset angles, even.
Yes. Yeah, which, I mean, if you don't do that, then you literally cannot. Right? Then all of flat Earth is broken, as our boy from 2019 was pointing out.
Right.
So, I mean, this is a kinematic model and describing sun angles for any observer over Earth, correctly getting the azimuth, which is the direction from true north, and the elevation, angle above the horizon, right? For any observer on Earth, that's the only way to do it, is to put a hemispherical view above the observer, call it an azimuthal grid, and give it dimensions of half of the known globe, right? So you see in a sphere a radius 3959, no matter how you want to look at it. And this model is a little bit bigger.
Yeah, so the entire sky is projected into that. This kind of looks a little misleading too. Keep it right here on this shot, on this view. So we see the sun and the moon with their GPs in the tropic, right? That's what that big, or I'm sorry, that's what the center sun is supposed to look like, right? And then we see these lines drawn to where it's going to be represented in our arc of vision in the as he dome there as he moves it along. But what's important to note is that there's not two suns here. We always see that corresponding GP sun, but this is how we see it in our dome of vision. So you can kind of like disconnect the idea that there's like two, right? So what we're looking at is we're only looking at the one sun, but this is how we perceive it relative to our latitude. This is extremely important because this resolves issues where people will say like, oh, we need two suns, there's three suns, all this kind of stuff. There's only one sun, and it's apparent for everybody in their own personal azidome, which is going to be at a different elevation angle relative to their latitude. And this is how it's perceived. But with that said, everything in the sky corresponds to a ground position. So this is what this is representing here to show you, like the sun's not overhead, in that dude's ASI grid at that latitude. It's, its ground position is still between the tropics, but he's perceiving it in this way where it's at the rim of his ASI grid. And that's what will look like. There's not going to be two suns. So I hope that kind of helps clarify that everything in the sky is projected into this little dome that Shane is zooming in on. There's no things above there to have bendy light rays coming towards you. That's just completely arbitrary. Everything is within this dome to begin with. So when it sets, it's just out of your field of vision. It's at that zero elevation angle, or it's, going behind a ball, however you want to conceptualize it. Either one, it's all representing the same thing, even on both models. That's why the bendy light rays and such had to be added to make it look preposterous, but there's no connection to those objects in the center going over the tropics versus where you're perceiving them. It's just to kind of keep you reminded like where the GPs are. Does that help?
Yep. No, that's definitely what I was going for. And that's kind of my answer to the problem laid out in the beginning when you said, we have to answer the problem of sun angles. I definitely agree. This is why this was the first thing that we built our premise on. It was the first thing I did a presentation on when I first came to Discord. It was my biggest talking point, is because definitely I saw that as a problem, as Zach did. And I just want to say that without this answering the problem for me, and then of course the math backing it up, the application being more logically sound and cohesive with our position, how it goes along with, what you could even do a null hypothesis with it, how it coincides with the celestial theodolite argument via the angles to the sky. Everything in the sky is always matching up based on flat Earth elevation angles. All of refraction just puts it back to the globe. All of the math corrections just put it back to the globe. All of the assumptions from the beginning just, already assume the globe. How do you first measure the globe? Well, you assume the globe.
Oh, a quick note on globe tilt assumption too. So remember, that was something to be solved as well. So how do we solve that? Well, the sun's elevation changes throughout the year. So if we just put everything that they put on the Earth back to the sky, the equivalence is there inherently. So the sun's elevation is going to change by 1 degree throughout the year, every day, until it reaches its minimum and maximum peaks on the, December 25th. And then it basically resets between the equinoxes, right?
Yeah, but so let's see. The best way to visualize the sun is, I think, from this panel, right? So the annual path of the sun, what it does is it goes from tropic to tropic, in and out, right? This is the analemma. You can see it in the top left. But what you're not really seeing is that it's changing height too. So it goes lower and higher like this. And if you're looking at it in your actual azimuthal grid over here, you'll see it do something similar, right? You'll see it. Actually, let's pick a better position. You'll see it do this, right? This is the sun over here doing figure 8.
That's so crazy. It makes a circle over the Earth, but you perceive it as a figure 8 in your ASI dome.
Yep. If you were to look at it from directly above, look at that. It just looks like a figure 8 in 2D, right? This is what we depict it as. This is what we think it is doing on its annual trek. But when you think about it, when it's changing seasons and changing light, and it's actually changing height quite a bit, where if you look at it from this, it's going down and out, up and down. And if we look at it, let's see from over here, you can see it doing, its actual path is more like this. Way up, down, in and out, right? For any observer, like that. So that's, and then when we're talking about where does the tilt come from? Well, this is actually based on the sun's ecliptic, right? The whole path of the sun based like this is not actually flat. It's based on a tilt, and because that doesn't work on this, because of the tilt of the axis, right? They had to tilt the whole world that corresponding degree to make the angles work, because they're assuming parallel light rays. So because of those two assumptions, that's why Eratosthenes also proved the tilt along with measuring the Earth by already knowing it. All right. So in conclusion, let's see. The problems for flat Earth, I think, have been addressed. Flat Earth angles to the sun only get answered with a azimuthal grid of vision with dimensions spherical or comparable to the globe, right? What they've always said. That's definitely the position. That's the only way that works. And of course, at the core of it, you can reapply Eratosthenes' supposed measurements to a more logically cohesive sound circle of the sun to accurately measure and extrapolate the thing you've been measuring the whole time. If you're going to look at the sun, measure the sun, your conclusion should be about the sun. You shouldn't be looking at the sun, measuring the sun, concluding about the Earth. That doesn't follow logically.
So if you need physicality for the heavenly orbs in the sky and their motions, then you have to assume these like vast distances to get these triangulations to work out for everything, right? To like get these points to line up.
Yep.
But if you're just using the latitude, longitude coordinate system, you don't need the lines to converge. Like you don't need that explanation, right? Because you can set to use that system, you're arbitrarily setting the height of everything to what it would be as you walk away from Polaris going south. Right. So
right. It maxes out visually the same. Yeah.
Yeah. So they didn't actually they had the same issue. They just solved it by saying ground ball, and then we're just saying eyeball.
Yeah, so they didn't really solve it. Like every problem that they solved, they just cheated, right? They were like, okay, we have varying angles for the distance to the sun. In real life, flat earthers are like, oh, that's puzzling. How do we figure that out? Like the real answer, I think, as we know, is that the sun is apparent and it's akin to like a source projection. It appears like a rainbow, right? A rainbow that follows you down the road. That's what the sun does. That's how it reacts. That's why it's tough to triangulate. That's why it appears in different spots. That's why they have refraction out of the yin yang for it. But it also comes to this. What I just put in chat right here. Let me go back to Discord. Is this like this differentiation between the globe and the flat Earth? Is these angles? You can either have a spherical Earth, like as our boy Zach said, you can bend the Earth down to solve the problem, or like you can do like that's the only way that solves it, and that doesn't really solve it because they say, oh, it's near parallel, so it's almost infinite, but not really. We'll just call it, 93 million miles or so, and then we'll know that actually it converges at a point somewhere that no one can know, and that makes it a real physical position that everyone can point to, and then everyone can also have a sweet apparent position all over the place, right? So that's why I said it's beautiful. The globe has solved it all by tricking everyone. All right. I don't know why I was so hoarse. I think I'm just getting sick.
Shane walks into a bar. The bartender says, "Hey, why the long voice, hoarse?" Sorry.
Oh my God.
Maybe he needs some brush-tail coffee. Hello?
What do you know about brush-tail coffee, madame?
Oh, you guys can hear me. Good.
I can hear you.
Anyways, go ahead. Lovely Prezi, Shanji. Thank you.
No, I'm done unless we have more questions or any questions.
Yeah, so they don't claim anything about getting that distance, that initial distance, that they need to get for their measurement to mean anything in the first place. There's no claims about that. I couldn't find any.
Nope, it's a scientific joke, as our mathematician lad liked to point out with his jolly chuckles. He was like, nobody knows, which probably like to say it was he paid his grad student. If you look at Wikipedia, they literally not invented a term, they use the real term, but their actual job is not to measure geodetic differences, it's to like count paces. And the theory that Eratosthenes, this guy was just followed around by professional counters, is folly, right? There was nobody. It's known that people say that. It's not known that there's any evidence whatsoever of that. So
Okay,
it's
so
all
you can
part of
throw
the
out
story.
that distance. That's fine. We'll throw out that distance. Okay. What about how do they communicate? Do we know how their cell phones got a signal when like I'm struggling on the expressway? How they got one back then before they had those gigantic cell phone towers and undersea cables? Do we know how they got a signal?
Yeah, this faster than light communication between Syene and Alexandria with Eratosthenes and his friend is still a mystery. It's another thing people like to speculate wildly about. I like to think there was like a canoe that could just go really, really fast, and they had it up this river, and it was going with the ether or whatever.
Okay, we're assuming telepathic communication. That's fine. Throwing out the distance, we're assuming telepathic communication. Now, you said we are going to get more into like substantiating whether these men existed. We can't substantiate whether these men existed. Can we substantiate whether the men who say they existed?
That's a very good question. Also, no, they're really evidenced in things like larger oral histories, things like Herodotus, the father of history, and other oral recountings, which are just other recountings of what, almost hearsay, pretty much historical record, oral tradition, handed down stuff. It's mostly myths and legends, right? So the same way you get the Greek history through a story of the Odyssey and the Iliad with the Trojan War and the gods coming down to fight battles, right? That's history. It gets mingled with the Greek and myth and Roman history. That's the same caliber with which you get Eratosthenes, Hipparchus, and the other fake Greeks. Yeah.
Okay, so we're throwing out the distance. We don't know how they got that distance. We know they communicated telepathically. We don't know if these people were real, or if the people that cite them were real, or if the people that cite them were real. Okay, so that's where we're at with this Eratosthenes. But we do know one thing, and that's for certain, and that's a globe. And because we know it's a globe,
He
because
summed
we
it
know
up.
it's a
He
globe,
nailed it.
Which
the
distance do
rest.
we not know how they got?
The distance between Syene and Alexandria is like the crux of the wonderful math that Eratosthenes did to measure the Earth. He measured the Earth by knowing this distance, apparently, but nobody knows how he actually knew the distance, except I know how he knew the distance. He looked at the sun and he calculated how fast the sun moves based on angular velocity, and did a calculation like they do today to say he did like the same way they get 1,000 miles per 15 degrees. Right? That's how they got the distance. That's how they got the globe model today. They're saying that actually he measured it by doing the same thing. when you know that they can just get it from the sun speed, then the motivation to make up the quoted story of how, well, no, it's not just from looking at the sky. We totally confirmed it on the Earth. Don't worry, guys. That becomes apparent. It's like, oh, we need a story for that. Behold, Eratosthenes.
If they know how many degrees per hour it moves or whatever, they still don't. How did they convert that into actual ground miles before they knew how big everything was?
The circumference, right? They just use the circumference, and then they use radial velocity via the radius, which you need a radius for, I think, right? That's how you get whatever 900 variance between 9 and 1,200 miles per hour ground position. Because you need a circle to get the velocity.
Yeah, but how did they independently get the circumference? Because obviously they didn't use. I mean, okay. They had to know they had to know the distance to Alexandria in order to get the measurement to find the circumference. But they would have had to know the circumference in order to get the speed of the sun in order to calculate the distance.
Also,
So that's it's not possible for either of those things to happen because they both have to simultaneously be true to use either one.
Yep, it's kind of similar to when Taylor was talking about the myth of abiogenesis and how RNA and DNA would have to simultaneously evolve in different and differing antithesis circumstances, but in a mutually beneficial relationship where they depend on each other. It's almost exactly like that. Yeah, well, obviously they had the dimensions beforehand, and they invented the story to prove the case, right? Clear as day.
No, I'm wondering where they got the dimensions from because they had those dimensions at least a long time ago, right?
No. I'm thinking 1700s. They measured the longitude. They got the systems. They put in place the prime meridian. They had all the sun measurements. They had the southern longitude map. Everything was set from there. So I'm just saying that they invented the story anywhere between there and now to prove that actually we've always lived on a sphere.
Okay. So they made up Eratosthenes in the after the border longitude met.
Yeah, that's my theory, and I think most of fake Greeks I'm with, because all these people that invented the tools for the thing that is the globe, but that weren't they were invented in like 200 and 400 BC. They sat around until the board of longitude needed them in 1700. Longitude was invented by Hipparchus, but was used in stadia, marked out by Ptolemy, but left to rot until 1714 when they applied it to the whole world based on the Greenwich prime meridian. So more than a little sus.
I mean, that covers my questions. I mean, we got telepathic fake Greeks vouching for telepathic fake Greeks vouching for telepathic fake Greeks.
Yeah, I think that they just thought if they threw like 6 or 7 of them at you, you'd have to believe them. Because what are the odds that all 6 are fake, right?
Yeah, it's a mystery within a riddle within a lie. Thanks, man. That was a good presentation.
Nice. Thanks, dudes. That was fun. Those are good questions. But yeah. Did we already do coffee commercial? Or you want to wrap up, Alan? You still going?
Liliana, tell me about that brush tail.
Oh, well, can you hear me? I always ask
Yes.
that.
Yes, tell me about that brush tail, please.
Oh, yeah, the brush tail. Well, funny thing is that I remembered there's something else that happened to me as a result of starting to drink brush tail coffee. And that is that before I started drinking brush tail coffee, I don't think I've shared this particular medical condition that I used to have before with you guys. But whenever I was like out, like at a store or a restaurant or whatever, like just out of the house somewhere, and if a really cute guy walked by me, all my hair on my head, which is shoulder length, would stand up straight like I'd stuck my hand in a socket, electrical socket. Anyways, when I started drinking brush tail coffee, that medical condition has just automatically gone away. So what can I say? I used to have big feet, now they're small. My hair used to stand on its end, now it doesn't. I'm telling you, there's some magic in that brush tail coffee. So folks, please go get your stash of the brush tail coffee before all the ETs and the zombies and all these different entities come and get them, because everybody's hearing about brush tail coffee. So hurry up and get it. Brushtailcoffee.com, right, Alan G?
It is brushtail.coffee where you can get brushtail coffee. Brushtail.coffee.
Thank you, dear. I
Oh, thank
always
you.
forget. Yeah.
Nailed
Sometimes
it.
I forget the web address.
All right, so we'll wrap this up and then we'll go watch our girl Liz on Strange World, I guess.
Yeah. And a disclaimer, we no longer claim that baby penguins were not harmed in the making of Brushtail. We no longer claim that they were not.
Gotta slam that optical equivalences, man.
Oh, what's going on? It's silent.
I think we lost Alan. I think you said to disconnect him when we're done. Wait, I remember that.